Good evening. Take a moment. Let me introduce myself. My name is Erin Deely, and I'm a very proud alum of the University of Arizona. Can we have a little love? Yeah. I'm actually headed to ASU U of A game in Tempe on Saturday, so send me your best wishes, or those of you that are going, right? I am the Assistant Director for Recruitment and Engagement, and this is engagement. And so I'm delighted to represent the College of Science, and I'm going to make a few announcements just about some other opportunities many of you have taken advantage of, but may not know the most up-to-date information. So I'm just going to flip through a couple of these things. How many have visited the Flandreau Science Center? Come back. We have a brand new exhibit if you haven't been there recently, and I should actually back up. Welcome to the fall 2015 SaddleBrooke Science Cafe. How many of you have been to the science cafes in previous? Awesome, wow, woo, we got a great following. So I'm new, not you. I actually facilitate a science cafe downtown at Borderlands Brewing, Cushing Street, and we also have Magpies on 4th Avenue. So this is one of 4 venues. But this is kicking off the fall 2015, spring 2016 season. And the series is, it's about time. Really fascinating. We're excited for this topic. I will point out, and I think many of you have already done so, probably picked up the brochure. And the Science Cafe brochures are by season. So this is just for this fall, and it lists all 4 venues, topics, titles, speakers, location, and times. So we do have one later this month, and then all of them will occur next month as well. And I'll make a few announcements about that. So if you haven't been to the Flandreau Science Center lately, our math department, what is one of the biggest gaps in education in our country? Math, right? Let's make it fun, engaging, and intriguing. So the faculty, graduate students, and undergraduate students got together and filled our exhibit hall with puzzles, problems, and proofs, and they're all hands-on. So if you haven't yourself visited or had family that's in town, go ahead and visit that. Also, since the early 1970s, we had not updated our technology in the planetarium. We now have a state-of-the-art 3D dome projection system. So it is spectacular. Real-time data can be incorporated onto that screen. You can see our hurricane happening, etc. All kinds of amazing things. But we have new shows, so please, visit that. How many of you visited Biosphere 2? All right, so how many have gone and seen this new promotion of the What If events that are part of the tour? Okay, so they're kicking it off this fall. I'm seeing what kind of reception. How many have been to the Desert Museum? Awesome, you guys are doers. Fantastic. I just mentioned it because what is exciting about the series we're presenting here through the Science Cafe is letting the public know and be involved with the research that's being conducted at Biosphere 2 and at the University of Arizona. And those what-if events pose questions to tour audiences, and then you get to interact one-on-one with researchers and what they're doing and ask questions and learn something more about our world. So if you'd like to take advantage of those, they're going to continue those on Saturdays, and they'll be doing those in the spring as well. So it might become a prominent feature at Biosphere 2. And there is a $2 off coupon on the back. And students are half off, so keep that in mind with the student ID. I'm not keeping up with the slides as well. I'm hoping many of you have also been to the Mount Lemmon Sky Center. Awesome. If you haven't, another brochure. That's a 5-hour program up Mount Lemmon. And if you didn't know, the College of Science just launched an app, the Sky Island app. So you literally can, through your phone or some kind of device, actually get a tour up the mountain through all the biomes. And then it actually indicates places to stop. So you can see examples of what they're talking about on that. And those are all available on our website. And every brochure has our website, cos.arizona.edu. So you can get information on all of this. Needless to say, they provide these tours about 5 hours. You get to get some geology, ecology of the region, probably a spectacular sunset, and then you get a star talk, and then you actually get into one of the world's largest public telescopes and have, basically a guide of the night sky. And those, the only reason they would cancel those has to do with inclement weather, right? You can't see the sky. So there's a link there so you can make reservations online or call Kathy Duncan, who is a fabulous lady. And then many know about our tree ring research. We're internationally recognized as having the biggest consortium of tree ring researchers. They used to be housed for decades in temporary housing in our football stadium. They now have their own building, and it's actually in the shape of a tree house. It's a beautiful building, and you'll notice there are bookmarks out on the table where hopefully many of you picked up an evaluation as well. But they have public tours throughout the week that are free. And if you don't have anything else to do, or you just have a real interest in tree ring science, they're always recruiting docents. So we could really benefit from your wisdom and experience and talents if you want to be involved in that program. And then we have Tumamoc Hill, which is the fourth location for our series of science cafes. Anybody walk up Tumamoc Hill or familiar with it? Right next door to A Mountain. It's a great hike, isn't it? That's a lung buster. Yeah, for that reason, we actually provide a shuttle to folks. You're welcome to walk up for that science cafe. We encourage that, but also because the road is closed to public traffic, that's the one science cafe that requires a reservation, so they can provide a shuttle for folks. And there's that amazing library, stone library, in those historic buildings that has a capacity. So just be aware of that. And we recently received a $20 million donation. So the best thing happening in our football stadium is this mirror lab. If you haven't visited this incredible facility, right now in production is one of the lenses for the Large Magellan Telescope. It's going to be it is going to be the world's largest telescope. So pretty amazing that's happening in the basement. Those are fee-based tours. How many have been to the Festival of Books? Okay, all of you might want to put down on your calendars March 12th and 13th. And I mention it because there is Science City, which is part of the Tucson Festival of Books, 10 tents of hands-on interactive activities, open houses. So the Mirror Lab tour is free and open to the public during that weekend. Everything's free and open to the public for the most part. And in January, and hopefully we'll have you return throughout this series, we'll bring flyers for that so that you're aware of when to do that. Those go first, right? People get in and get those free tickets, and those go first, but I want you to be aware of it. And one thing that's not on our website, but all of our departments have pretty amazing lecture series on a smaller scale. And so if you're interested in astronomy and things that are happening at the Stewart Observatory, there's also a flyer out there for their public talks, which are very popular. And just so you're aware, and many of our community members aren't, those of you that want to visit all these venues that have a fee associated, whether it's Biosphere 2, the Mirror Lab, as well as Flandreau Science Center, there's an entrance fee, as well as for the dome projection shows. You can actually get a 3-for deal. So we want you to be aware of that. If you're going to visit all of those venues, you certainly want to take advantage of this deal. And again, go to the website. All of this is here. Well, everybody take a deep breath. I know you're here for another reason, not to listen to me promote the College of Science, but we're really blessed to have a great speaker tonight and a series of 6 outstanding speakers. So I will give a brief introduction. I also want, those of you that have been to the lecture series, have you caught wind of what the theme is? You want to hear? Okay, we got a few folks. This won't come as a surprise. I mean, it's international news on a regular basis. But they put together a group of speakers to discuss the global climate change issues. So that will be the theme for the spring. And we're still waiting on exact dates, but affiliated with the College of Science website will be the lecture series website. And so we'll get those dates to you probably next month at this. You can continue to visit our website if you like. And just to remind you about the format tonight, we'll introduce our speaker. He'll give a fabulous presentation. And then myself and Barbara Kahn, who is also in the audience with the College of Science. Hi, Barbara. We will then work the audience to get the microphone to those of you that have questions. And for a brief period of time after that question and answer session, Pierre will be available for just some one-on-one questions if you still have them. But he has a drive, so let's just be mindful of that. And last but not least, I'd like to thank the DesertView Performing Arts Center staff. We've got Darby, Ronnie, and Ruslan, who's running the show behind the scenes. So please, a round of applause for those folks. All right, so now for the meat of the program. So you know the topic is, it's about time, and our speaker is Dr. Pierre Meystre. I'm not good at French, only Spanish. He's a Regents professor, and he's the director of the Biosphere 2 Institute, the research arm. And I'll just give you a few bullet points about him. He obtained his physics diploma and PhD from the Swiss Federal Institute of Technology in Lausanne, Switzerland, and the habilitation in theoretical physics from the University of Munich in Germany. He's a Regents professor of both physics and optical sciences at the University of Arizona. And his research interests, which will be reflected in this talk, include theoretical quantum optics, atomic physics, ultra-cold science, and quantum optomechanics. Yeah. I did ask him to share a little personal information, and I think many of you might have this same kind of affinity. He has a love of great food and great wine. And one of his more serious endeavors is making his way through the vineyards of the world, especially those of Burgundy and southern France. So without further ado, Pierre Meystre.
So good evening, and thank you very, very much for taking the time to spend an hour or so talking about some physics. I'm really always so impressed. I travel a lot, not just to southern France. I also go to Napa. No, I go to the East Coast a lot, and I have friends in some of these universities there, and I tell them that we have these science lectures where we attract 2,000 people, and say, you mean 200, right? So they can't believe how great it is a place for science and the interest of science in Tucson area. So it's really exciting, and thank you for being such big fans. So I'm going to talk about time a little bit, and let me see if this works. I'm a theorist, so I'm not very organized. Okay, so can you see that in the back? Okay, so here it says that 2015 is actually a very, very special year in physics. One of the reasons, which you've probably seen on television, is that it's 100 years of the theory of general relativity by Einstein, which is one of the great theories of humanity, really. But it's also the International Year of Light. And these two things are actually very, very, very connected, very closely connected. And what I want to try to do this evening is to show you a little bit why it's connected and why light is so important when we want to talk about time, and why it's all very confusing. So what I'm sure I will show you is that for physicists, time is something which is not very, very simple, but I'll try to give you a simple reason why it's not simple. And the person who needs to be thanked most for having created this really fascinating confusion and this really very profound understanding of how complicated time is this young man, okay, Albert Einstein. So he was an amazing person, and again, 100 years ago, he created this theory of general relativity, and in 1905, before that, he did the special theory of relativity, which already brought this concept of time into a very new view, which is still very complicated for everybody to really grasp. So let's talk a little bit about time. And the title of my talk is It's About Time. It's also the title of the series. I think you stole it from me. Yeah. And there's an echo a bit. I have to be careful. Okay. And here, oops, let me go back. This is a clock which is in the old town of Bern in Switzerland. And the reason why this clock is on this slide will become a little bit more apparent, but The urban legend is that Einstein actually looked at this clock every day when he was going to work at the patent office, and always looking at this time was an inspiration for his work. And I like this clock also because I was born very close to this place, so it's like a back home. Okay, so time. So time is something that everybody has worried since the beginning of times, really. Because people, farmers needed to know the seasons. And so they looked at the sky. And this is why there's been a very, very detailed understanding of the motion of the planets and the stars from the very early days. But it's not a very accurate concept of time. It's something which will tell you about the months, maybe the seasons, when you have to plant, when you have to harvest, when you have to do these things. You can become a little bit more accurate and have an information about the time during the day by using a sun clock, for instance, right? Which will give you a pretty good, accurate, within a few minutes of what time it is during the day. And then you get a little bit better. So this is something that we can still use in our kitchen to make eggs, if we don't have an iPhone. And then you can buy a beautiful Swiss watch. And if you are very rich, and you are really a geeky physicist, you can build an atomic clock, okay? And this is a picture of an atomic clock, which is quite big. It's hard to take in your car. This one is actually in Boulder, at least not very far, at least in Boulder, not very far from here. But what you may not know is the accuracy of this clock, of the best of these clocks. And the best atomic clock now is accurate to better than 1 second in the age of the universe, which is extraordinary. Okay. And if you want later, we can talk about why bother. Okay. But there are good reasons to do that, and we can talk of them later if we have time or if you want to. Okay. So why do people care so much about time? And the reason, one of the main reasons why people have been worried about time since the Middle Ages is because they wanted to go places. And navigation was a very, very important issue. And one of the big issues that people had when they tried to discover the new world was, for instance, to figure out where they were. And they could understand pretty easily where they were north and south because they could really look at the northern star and figure out where they were. But between east and west was a much, much bigger problem. Okay. So there was this problem of longitude, and boats didn't know where they were, ships didn't know where when they would crash, they would get lost. It was a major, major problem. It was such a big problem that in 1714, the British Board of Longitude, so they had a committee just to worry about this huge problem, came up with the longitude prize, which would be given to the person or people or persons who should discover a way to measure the longitude. Okay, that was how important an issue it was. And it was actually much older than that. The French Royal Academy offered also prizes for navigation, but earlier in Spain, which was another major empire which wanted to figure out what other land to steal, they also made this prize. And in Holland, everybody was very, very worried about this premier longitude. And it became quite clear quite soon that it was the same as trying to figure out what time it was where you were compared to London, or Paris, or Madrid, or wherever you were, Lisbon, or wherever you were. Because if you are someplace, you can look at the sun setting, and if you know what time it is compared to London, and you know the time in London, you see how far you are from London. So by having a clock which told you exactly, which would keep track of time very well, you could in principle solve this problem of longitude. And this is the man who actually solved it, John Harrison. And he developed over the years, it's a fascinating story. If you have time, you should go, and there are several books about the story of John Harrison. And he developed some clocks. This was the first model of a clock that he had. It was a very big thing. It was a bit like that. And it didn't work really well because it was not stable enough to be on the ships. But after 5 models, about 30 or 40 years, he came up with this wonderful clock, which was accurate to within a few minutes over crossing the ocean, which is pretty amazing. And if you look at watches that you can buy now, they look still very much like this watch. Okay? And everybody kind of agreed that it was a great solution, but nobody wanted to give him the prize. So he actually never received the prize, which is very, very sad. I'm told, I've not seen, but I'm told that this clock still exists. It's on an exhibit in London in a museum, but it's not being run anymore because they don't want to write down. But in principle, it still works. Now, we still use time to figure out where we are. And this is actually a very important statement, that to measure distances, we measure times. Okay. It turns out that the meter, or yard, or whatever, is not a fundamental unit. The fundamental unit is time, and we connect time to distances with the speed of light. This is the official international definition of the meter. The meter is defined as the length of a path traveled by light in vacuum during a time interval of 1/299792458 of a second. Okay. And there's some complicated reasons why it's this number, but it's the definition of the meter. Okay. So if you know your time, you know your distances. Okay. So again, the second is a fundamental unit, and the meter is a derived unit. And if you are really geeky, this is the definition, current definition of a second, but I'm not going to go there. And in fact, that's how your GPS works. Okay, your GPS doesn't work by measuring where you are compared to downtown Tucson. The way your GPS works is by having a bunch of satellites around the Earth, and every one of these satellites has an atomic clock on it. And actually, the Office of Naval Research knows exactly where these satellites are. And what these satellites do is that they send light to you. Actually, it's not light, it's microwave, but it's the same thing. And you try to figure out, you also have a very accurate clock in your iPhone or in your GPS in your car. And you measure very carefully the time it took for the light to go from this satellite to your car. And now we know the speed of light. It was this 1/10, it was this 300,000 kilometers per second, roughly. So and we know where the satellite is. So if we know how long it took for the light to go from the satellite to you, you know that you're on a sphere, which is at some distance from this satellite. So if you're in satellite, which is here, you know that you're on this sphere. You're somewhere on that sphere. It's not very useful because you'd like to know exactly where you are. So then you can take two satellites. Thank you. And if you take two satellites, you know that you will be at the intersection between these two spheres. And if you take three satellites, then you will be down to 2 points. And normally you know that one of these points is not a good solution. So that's how you know where you are. That's how a GPS works. A GPS works is by sending you these signals for three satellites, and the intersection of the distances tell you where you are. I told you, you need to measure times. You need to measure the time which it took for light to go from the satellite to your car. How well do you think you need to measure this time? Okay, you'd like to know where your car is more or less within maybe a few centimeters, a few inches, so you don't drive into a wall. So you can do some little calculations, which are not very hard to do. And if you have a clock which is accurate within the thousandths of a second, you will know where your car is to within 200 miles. So it's not great. Okay. So how much better do you have to do? Suppose you have a clock which is accurate to a millionth of a second. You will know your distance, your position within 1,000 feet, which is still not great, right? Instead of parking at Basha, you may park inside Basha. Not so. So it turns out that you need a clock which is accurate to billionths of a second. And this is basically what you now have to have in every iPhone that we have in this room and every car which is a parking has to know how far it is from these 3 satellites with an accuracy in time of about the billionths of a second, which is extraordinary. Okay. Okay. If you do that, you're accurate to within about 1 foot. So this is just a little introduction to show you that times and distances are really very intimately connected. And if you want to measure distances, you almost always measure times if you want to do serious measurements. Okay. All right. So now it's going to get a little bit tricky. So I want you to take a deep. Just relax. It's not going to be bad. It won't hurt. Okay. Let's try to do something. Okay. And we're going to do a little. So we are going to start with a little problem that we all know how to solve. We're going to take a train. And the train is moving, let's say, I'm always using metric units. I'm sorry. I was born on the wrong side of it. So it goes at 30 kilometers an hour, okay? And now there is some character who is in the train. Maybe it's Clint Eastwood, so he's running on top of the train. Anyway, here's this character, and he's moving at 5 kilometers an hour relative to the train. So if you are sitting on the ground and see this person, how fast do you think this person will go? We know that, right? You just add the velocities. So it's 30 kilometers an hour plus 5 kilometers an hour. We all know that. Okay, this is something we learn in high school. Everybody is very happy with that. So now let's say, well, this guy is a bit faster. Okay, so let's say this guy goes at the speed of light, which is roughly 300,000 kilometers per second. So it's not, let's say it's light. No, it's not a person, it's a photon. Okay? And the train is still going at 30 kilometers an hour. So if you're sitting on the ground, how fast do you think this guy is going to go? It's the same thing, right? You add your two velocities. It's 30 kilometers plus the speed of light. That's what we learned in school. No. Okay. That's not true. And that's a problem because it tells us that this issue of addition of velocities is no longer true. What you will find is that this person, relative to the ground, will also go at the speed of light. Okay? Nothing can go faster than the speed of light. Okay, so as they would say, we have a problem. So we have to figure out a way to deal with this problem. And the person who solved this problem is, again, this man, much younger now. It was a picture taken when he was working at the patent office in Bern. And he came up with this very, very profound statement, which has very, very disturbing consequences, which we'll get through, which is that nothing can go faster than the speed of light. And the speed of light is the same for all observers. Whether your light is, you look at it from inside the train or from outside, speed of light is always the same. So what I'm going to do is to show you a little video. And this video will kind of try to explain what's going on. And I think it's a good video, but it goes a bit fast. So we'll go through this video, and then we'll revisit it a bit more slowly with just little graphics on the projector, okay? So let's try to see if it works, and most importantly, if the sound works. Let's try that. So I stole that fair and square. Okay. But I was told by the College of Science that I wouldn't go to jail.
Regardless of the speed with which they themselves are moving, all observers measure the same speed of light. To an observer on a platform, for example, this train's passing at a good clip. But to someone on the train's speed seems to be 0, and and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion. 1905, Bern, Switzerland. Einstein, a young physics student supporting himself as a patent clerk, finds himself disturbed by seeming inconsistencies at the very core of physics. He sets forth two fundamental postulates. The first is Poincaré's relativity principle. The laws of physics are the same for all inertial frames. His second postulate states that the speed of light is the same for all observers. He simply assumes the phenomenon that Lorentz has been struggling to explain. From these two postulates alone, Einstein deduces exactly the same equations Lorentz discovered earlier.
Want to go through equations, right? It's too late in the evening. So it went a bit fast. So what I'm going to try to do is to do it again slowly, and hopefully you will be even more confused. No, hopefully not. So what I'm going to do is to draw something called space-time diagrams, and this sounds really fancy, right? It sounds really complicated, but it's really simple. So what I'm going to do is I'm going to assume that space has only one dimension, because I don't know how to draw these pictures in 4 dimensions, which would be 3 dimensions for space and 1 for time, right? So it's not going to work. So space is just 1 dimension. And I'm going to draw it on this horizontal axis, position, and here I'm going to put time. Okay, time, so time goes from here, goes up this way, time runs, okay? Position, you can go either this way or you can go that way. So for instance, you could have Tucson here, you could have Phoenix here. Okay. So people move in space-time. Okay. So for instance, we can have Bob. And Bob is going, where is he going? He's going toward Tucson, right? See his position, time goes this way. So as time moves up, his position becomes closer to Tucson. So he's going from Phoenix to Tucson, right? At some speed, okay? And the faster it goes, the flatter that would be, okay? Because it can go in less time. Now we can have also, who did I use? Alice, okay? And we always use Alice and Bob in theoretical physics. I don't know why. We used to call them A and B, but we want it to be. So now we have Alice, and Alice is going from Tucson to Phoenix, maybe to the game, right? And she's going faster because it takes her less time to go from here to here, see? But now there is a situation which is very important. It is when they're both at the same place at the same time. And we'll need to really keep that in mind. So here, see, Alice and Bob are at the same place at the same time. So this is when you have a collision. And it's important to keep in mind for my next little discussion. Okay, so that's all we're going to use, these little space-time diagrams. Okay, people going this way or that way, and then they can collide, or maybe they don't collide. So, all right. So this was just to set the stage a little bit. Now let's look at this video. Let's try to repeat what it said. If we have a person at rest, the position of this person doesn't move, so time just flies. The person stays in the same place, so a space-time diagram will be vertical. If the person moves, that's how the space-time diagram will go. This person is moving from here to here in a time which goes from here to there. And now what we learned from Einstein is that nothing can go faster than the speed of light, so nobody can be here. Big no. Okay. And in physics, when you say you can't do it because it's the law, we mean it. Okay. All right. So light can also go in the other direction. Instead of going from Tucson to Phoenix, it can go from Phoenix to Tucson. So we have a cone here. In 3 dimensions, be some kind of a cone where things can happen. Okay. Outside this cone, for this person here, nothing can happen. This person cannot communicate to this region here. All right. So that's what we have. Again, what I just told you as to the second time. And now we're going to have our Einstein, Albert, and Poincaré. And let's assume that we're sitting in the same little cart as Einstein. Okay, so he's not, and so we are not moving. Okay, we are in his cart. With respect to this car, we are not moving. So as a function of time, this wheel will just stay at the same place. This wheel will just stay at the same place. Poincaré is moving, okay, let's say from left to right. So this wheel of his cart will go this way, and this wheel of his cart will go that way. Now there's this flash of light. Okay, so suppose I'm sitting with Einstein. Let's pretend I'm Einstein, okay? It's kind of fun. All right, so light for me goes at the speed of light, and I send a flash of light, so it can go in both directions. So the light, oops, going too fast now. Let's start again. So here's the light, which I send this little flash of light, and it's going to go either this way, if you go forward, or this way. Actually, it's going to go both, because the flash of light goes in both directions. Now remember my collisions. If something is the same place as something else at the same time, you have a collision. So look at this. This is light going this way, and here, this is this wheel, okay, of Einstein. So when light arrives here, it will collide with this wheel. When light arrives here, it will collide with this wheel of Poincaré. So now we can see what happens. The light starts, flash of light, the light starts to propagate this way and this way. At the first time, it will arrive here. So Poincaré will see something on this detector. A little bit later, the light will arrive here and here. So Einstein will get a click here and a click right here on both of the wheels of his cart. And a bit later, the light will arrive at the position of Poincaré's cart, so the light will arrive here. So you see what happens is that for Einstein, light reaches both sides of his cart at the same time. But for Poincaré, the light arrives earlier than for Einstein at one of the sides and later at the other side. Okay. So that's what they were telling you in this thing. So two things which happen at the same time for Einstein do not happen at the same time for Poincaré. Now let's say, well, let's sit with Poincaré instead of with Einstein. So we can so now Poincaré is not moving, and Einstein is moving backwards. So his velocity now makes him go from right to left. And again, we have the flash of light. So the light will arrive at the position of this wheel of Einstein first, then it will hit the two wheels of Poincaré, and then it will be the other wheel of Einstein. So they see the same laws of physics, but they don't see things happening at the same time. Okay? So it's very, very weird, which is why time is kind of a very complicated thing to digest. And this can be summarized in this sentence. Okay, what is now for me may not be now for you. Okay? My now is not the same as your now. Your now can be what I consider the past, or it can be what I consider the future. Okay? And so you have this very, very simple idea that nothing can go faster than the speed of light, and you get this crazy consequence, which has been tested. Okay? And by the way, if you don't account for this effect in your GPS, you will wind up inside Basha. So this is serious physics. So now simultaneity loses its meaning. So that's why time is such a complex, complicated, subtle issue in physics. And that's why for students, it's very hard. Actually, it's still very hard. You know, I've been in this business many years, and it's still something which is very, very counterintuitive. Okay, so let's change topic for a little bit. I'm going to talk about cosmic rays. Why do I want to talk about cosmic rays? Because cosmic rays are very, very fast. They move essentially at the speed of light. And when they arrive in the atmosphere, they kind of make all kinds of nasty collisions and all that. And one of the things that they create is something called a muon. And don't be scared, muon is kind of like an electron, except it's a bit heavier. Actually, it's 2,000 times heavier, 200 times heavier than an electron. And these muons, they move essentially at the speed of light. And you want to have things that move fast to test relativity, okay? Because this effect I'm talking about don't happen if you walk 5 kilometers an hour. They happen if you are close to the speed of light. So these guys actually move at most of the speed of light, and they also die. So we kind of have a clock. We have a start and an end for this system. Electrons don't die, so it's harder to do experiments in a sense with electrons for what I want to do. So we're going to have these muons. They're kind of like electrons. They move extremely fast, and they die after 2.2 microseconds. Okay? All right. So this has nothing to do with my talk. The reason I show it to you is that this is the place where some of the very early experiments in cosmic rays were carried out. This is an observatory, and the reason I show it to you is twofold. First of all, it's very beautiful. And second, it's in Switzerland. So this is in the Alps near Bern, actually not very far from Bern. This is a huge glacier in Switzerland. It's called the Aletsch Glacier. And this is called the Sphinx Observatory. So anyway, that's why I showed you that. But let's get back to our cosmic rays. So I told you our cosmic rays, they will die. Now, they will not all die exactly after 2.2 microseconds. They have a 2.2 microsecond is the average lifetime. Half of them will live longer than that, and half of them essentially will live less than that. And the distribution of, it's just an exponential, okay? Very much like everything else. If you wait long enough, everything will be dead, but there is this probability. Okay. All right. And there is a half, the so-called, we call it the lifetime, but it's really the half-lifetime. The average half-lifetime is this 2.2 microseconds. So now you can do experiments with these guys, okay? And you can maybe do experiments in mountains. And again, it's kind of a chauvinist thing. This is another beautiful Swiss mountain. It's the so-called Eiger. This is the Mönch and the Jungfrau. And actually, this observatory I showed you before is right there. And now you can imagine, suppose that you have 1 million of these muons in the sky. at 4 kilometers from the Earth. Okay? Once they arrive on the Earth at ground level, how many will be left? Okay? So we know how much time it takes for them to go from 4 kilometers to the Earth, right? To the level of the, the valleys. And it's very easy. Again, it's freshman physics. The time is the distance divided by the velocity. We know the distance, it's 4 kilometers. We know the velocity, it's the speed of light. We can do the division. And we know how much time it took. And then we look at this curve and say, the time was, let's say, in this units is here. So the prediction is that we will have that many neurons left. Okay, so you do the calculation, and then you do the experiment, and you find this. Okay, and this is again this business of relativity, and the time depends on who looks. Okay, and this is actually one of the early experimental quantitative proofs of the fact that I told you before, that things which happen at the same time for me may not happen at the same time for you. Time can be longer or shorter depending on who is looking at what. And here is the statement again: for an observer on Earth, the clock of the relativistic neurons runs much more slowly. Okay. And this is the statement, and this has been tested. And this can be an enormous difference if you actually are at very, very high relativistic speeds, very close to the speed of light. So again, I arrive at the turning point of my presentation, which is here. Okay. So I'm pretty sure that unless you have a background in science, many of you at this point will be confused, and it's okay, because you should be. And there is nothing wrong with being confused a little bit about that. Okay. All it means is that you need to think more about it, that there is a beautiful problem, there is a beautiful thing that we don't quite understand, and which means the time is in many ways in the eyes of the beholder. Okay? And so when I ask the question, what is time? The answer is, well, it depends. Okay. It really depends. Okay. And this is a beautiful sentence that Brian Greene writes a lot of very interesting books on physics. He's an expert on string theory. And he says, what is my main message here is that relativity challenges the basic intuition that we have built from everyday experience. It says that our experience of time is not what we think it is, and that time is malleable, it can be stretched, it can be compressed, okay, depending on what you do, how fast you move relative to whom. And the same is true for space, actually. Space and time are two components of the same thing. We always talk about space-time. So this is really the lesson that we've learned from Einstein. And this allows me to go back to the clock. Now you see the whole clock. And Einstein's apartment actually was right here, more or less. And every day he would walk by this clock to go to his office, the patent office. So here it is. All right. And now I'm going to play my Steve Jobs. There's one more thing. Remember, Steve Jobs always did that when he was presenting his new stuff. Here's one more thing. And the one more thing I want to tell you is that we also need to talk about energy now for a minute or two. Okay. We've talked only about time and distances, but also want to tell you there is something else we need to keep in mind, and this is energy. And one of the other things that quantum mechanics tells us is that we cannot be too greedy. You're not allowed to be greedy in quantum mechanics. If you want to know something very well, something else will not be known very well. This is something which, again, for the experts in the room, is called the Heisenberg uncertainty relation. If you want to know a position very well, you cannot know the velocity very well. If you want to know the time very well, you cannot know the energy very well. Okay. So if you take an energy uncertainty This is a Greek letter, we call it delta, and we always use this kind of letters in physics just to confuse the audience. So this is the uncertainty in energy, delta E. This is the energy in time, let's call it delta T. And what quantum mechanics tells us, if I take delta E, and if I take delta T, and I multiply them, the product is always larger than a quantity which we call h bar. Okay, h bar is again something we like to use to confuse people. It's just a constant. It's called Planck's constant, and it is a very, very small number. I'll show you this number a little bit later. But what it tells you is that if you want to know something with very, very little uncertainty, okay, a very, very small time interval, then you will have huge problems with the energy. Your energy can become absolutely enormous. Okay? And this is again what I say here. This is the Heisenberg uncertainty relation. And very, very short time intervals correspond to huge energy. So now let's refresh our memory, because I'm going to use huge numbers and very, very small numbers. And another thing that physicists like to do in addition to confusing people is to write as little as they can. We like to be lazy. So we have this kind of notation. If we want to write a very, very big number, like a quadrillion, we're not going to write all the zeros. We use this very, very compact notation. We just mark how many zeros we have after the 1. So for instance, 1,000 would be 10 with this little c, 10 to the 3. 1 million would be 10 to the 6. 1 billion would be 10 to the 9. And if you go to very, very small numbers, we use the same trick. 1,000 would be 10 to the minus 3. See, the 1 is in third position after the decimal point. 1 million is 10 minus 6, and 1 billion is 10 minus 9. So this just makes things convenient. There's nothing to it, it's just notation. But it will be very useful when we start looking. Oh, I have h bar, by the way. For the h bar, there is some units, which are not important, but the thing, you cannot read it in the back. It's 10 with minus 34. So what it means is that there are 33 zeros here, and then there is this 1. So it's not a big number, okay? But it's really important, okay? Because if this number were 0, your transistors would not work. Okay, anyway. So now that we know these small numbers and these big numbers, we can look at the history of the universe. Kind of a simplified history of the universe. But let's go through a couple of things on this graph. Again, I hope you can read it in the back. Here there is something we don't really know what it is. It's the Big Bang. Okay, and then there is a period which was called the inflation period, which we thought as a community that had been demonstrated in experiments published in the spring, but now there are some doubts about that. So more measurements need to be done. And if you look at the times here, so here we don't really know, but here is 10 to the minus 44 seconds. So again, it's 0 point and you put 43 zeros. So it's a very short time, okay? And here it's 10 to the minus 37 seconds. It's still a very, very short time. Okay. I think next lecture you will learn about the cosmological calendar, and you will kind of maybe get a better feel for how tiny these numbers are. The problem is that if this time interval delta t is very, very small, it means that the energies are huge. Okay, the energies you can have are huge. And this is why the physics in the beginning of the universe is very, very complicated, because it's high energy physics, we don't understand always as well we would like. So the energies that we have here for this time are again the energies of these cosmic rays, the high energy cosmic rays. So I say, well, let's just study cosmic rays and we can study what happened in the beginning of the universe. And the answer is not so fast, because cosmic rays have a problem. I don't want to go in great detail through this curve. All I want to tell you is that this is a measure of the energy of the cosmic rays in some units. The more energetic, the closer they are to here. And here is how many cosmic rays land on the Earth okay, for this kind of energies. And we would like to look at things around here. And if we want to see cosmic rays with energies which are relevant for the very, very early stages of the universe, we get about 1 cosmic ray per square kilometer, which is more or less a square mile per year. So you have basically nothing. You have to wait thousands of years before you have some kind of a signal. So that's a problem. This is a problem that people in physics are trying to solve. There is this observatory which is built in Argentina, which will be 30,000 square kilometers with about 2,000 detectors, but even then they will get only a few events per year. So you can't really do good physics there. So we have to be a little bit less ambitious, and we're going to say, well, let's go a little bit later during the creation of the universe, let's say a tenth of a billionth of a second after the Big Bang, more or less. And here, we can actually build this system. We can build systems, it's called accelerators, which provide the kind of high energies which correspond to this time. Since the times now of delta t is longer, the energies are lower. And this is what people do, for instance, at CERN in Switzerland. Again, it's always in Switzerland. This is Geneva, right here. This is the Mont Blanc. This is France. Swiss people are very unhappy about that because this is the highest mountain in Europe and we wish it were in Switzerland. Anyway, and this is Lake Geneva. And anyway, CERN is here. This is this big accelerator which has a radius of 27 kilometers, which is about 16 miles. And this is the place where they've seen the Higgs boson. You've probably heard about that a couple of years ago. And the thing that I wanted to tell you is that this Higgs boson, are you trying to kick me out? I'm almost done. All I wanted to say is that these Higgs bosons, let me go back. She got me all disturbed. Which correspond to these very, very high energies, which are things which happen at the beginning of the universe, have a duration of 10 to the minus 22 seconds, which is again 0.21 zeros and then 1. And that's, so these things last basically no time at all, and it's a big problem. So, but anyway, they've done that, and by looking at very, very short times and at very, very long energies, they were able to look at things which happened 13 billion years ago, which is really amazing. What it tells you is that these accelerators, which connect the cosmic origins to the shortest time we can think of, is both the world's most powerful microscope and also the greatest accelerator, largest telescope. But since I'm running out of time, did I tell you that time is relative? Okay, so let me try to move along a little bit and come back to the real world, okay? The real world being what the world we live in today. And we started here, where we started with telling about how complex the concept of time is, and then we talked about what happened for very, very short times with their huge energies. But then, of course, time evolved, and at some point the solar system was formed, and then the Earth was found, the first fossils came in, and then the dinosaurs, the Rocky Mountains were formed, and here this is the logarithmic scale, so this is essentially 14 billion years, and this is just millions of years, so it's it's just the last minutes in the life of the universe if it had the scale of a year. And all I want to tell you here is that we are going to take this trip together. Tom Fleming will talk in 1 month about cosmology. And then in January, Jessica Kapp will tell us about geological times. And then Brian Enquist will talk about biological time. Then we will have physiological times, which I know nothing about, obviously. And then another physicist will talk to us about how we can study extremely fast processes in atoms and in molecules and things like that. So just to show you a little bit more, and I'm really almost there. The timescales that we're considering, we started with the age of the universe, which is 10 to the 18 seconds, more or less. And then we will talk about human beings, and we basically all live about 10 to the 9 seconds. Some people live a bit 2 times 10 to the 9, sometimes. So there are fluctuations, like for the neurons, right? and we will talk about that. And then we have another time scale, which is the time of second, that's our heartbeats, okay? And then we have nanosecond, microsecond, nanosecond, which is protein folding, okay? And then we have something called attosecond, which is the time it takes an electron to orbit about an atom. And we will have 3 lectures on that. Fabian Hernandez and Brian Enquist will be working in this kind of human timescale where we kind of understand how things are happening. And Arvind Sandhu will tell you how we can get there. So that should be a lot of fun. And the way Arvind Sandhu does that is, how can you look at things which are so fast? Okay, we can do a second, we can do a week, we can do an hour, it's the human scale, but how can you do an attosecond? And the idea is you freeze time. This is something which has been known for a long time. There is a very famous Muybridge picture which had to do with whether a horse had a stage in his galloping where all legs were up in the air. He had actually a bet with Stanford about that. And he developed this fantastic technique where he had a bunch of cameras and strings, and the horse would run through these cameras and he could make these extraordinary pictures. And now we can do beautiful pictures which are mostly fun, okay? And if you want to go to the kind of things that Arvind Sandhu is going to talk about, you need to actually freeze time in different ways, and the only way we know how to do that is with lasers. And some of the lasers that are being used to do that are actually rather big machines. I just wanted to show you a picture of this laser, which is the so-called LCLS, a linear coherent light source, which is at Stanford University. And it's kind of a nice story that Stanford got Muybridge to start doing these pictures, and now the fastest pictures of nature can also be done at Stanford. Okay, so it's kind of closing the loop. This is actually not a cheap laser. But a lot of things can also be done in a laboratory, as Arvind will tell you. This is not a picture of his own lab, but his own lab would look very, very similar. And you can freeze time and see the kind of things that I have listed here. Okay, and he will talk about that. It will be the last lecture, is that right? In March, I think. April? Okay, in April. Okay, yeah, because it's 6. So, yeah. Okay. You know, theories kind of factors of 2 are not very important. All right, so here is a summary of these lectures. Make sure you come. You will have a lot of fun. It's really great science, I think. I think it beats working. And let me just leave you with 3 kind of take-home thoughts that I wanted to share with you. The first one is that curiosity-driven research is really great, and it will lead to places you don't know. Think of Einstein worrying about time, worrying about simultaneity, and now it's running your GPS. Who would have thought, right? This is really absolutely amazing. So it is so important to keep funding curiosity-driven research. You never know where it's going to take you. And asking simple questions can take you to through incredible paths. Okay, you ask, what is time? And you realize, I kind of know, but I don't know. And that's okay, because it brings more and more questions, and you understand more and more things. And eventually you can build a GPS, or you can build an MRI system, you can do a transistor, you can do whatever, okay? So never forget to ask simple questions. And the last thing I wanted to say is that we are really happy not to know. It doesn't bother us. Okay, a lot of people tend to be worried, to be concerned, and very distraught when they don't know the answer. Scientists strive on that. Okay, that's our business. We really want to ask questions where we have no clue what the answer is and try to figure out the answer. And this is why we really are very comfortable not knowing the answers. That's it. So thank you very much.
So just before we end my apologies, I have a booming voice. As Pierre mentioned, we do have a talk December 17th next month. I do want to mention, I know it's over the holidays, and we'll also be back January, February, March, and April. This series is available on the College of Science Cafe website, as well as a brochure. We're also being filmed right now, meaning our presenter. And on YouTube, this is available. So if you can't make one of these talks, this is a simulcast on the YouTube. And on the flyer on the table outside is the link. And you simply visit that link through your internet browser. And at the prescribed time, you can watch it. And then you can visit and see podcasts from that. It's the DesertView Performing Arts YouTube channel. So they'll be stored there. I do want to also mention, we are going to take some questions, but we are over time. But I would love for the audience to be able to do that, as well as those of you that do have evaluations, and there are some left out on the table with pencils. Not only do we want to hear your feedback, because we share that with our speakers who want to improve and enhance what they provide to the public through venues like this, as well as we like your ideas of things that you would like us to bring from the U of A of interest to you. So please fill in those. We actually look at them and then coordinate speakers based on that. And also, if you want to hear about talks like this, we're not going to solicit money or commercials. We just want, if you want to learn more about opportunities like this, we'll add you to those announcements through a listserv. Okay, so with that, I'm going to ask Pierre to be the one to see the hands go up when we see one. Please ask your question, hand the microphone back, and then Pierre will respond.
Thank you for a great presentation.
Yep.
So you've mentioned, and we've heard throughout our lives, that the speed of light is constant.
Right.
And yet, when Einstein was working on quantum mechanics, quantum theory, you know where I'm getting.
Yes.
So not all the pieces fit together really well.
Right.
So he came up with spooky variations, very scientific term, spooky.
Right.
And in this bell in between working on it recently, and I probably am butchering the name, the University of Delft, is it?
Right.
Just very recently,
yes,
believes that they have measured something faster than the speed of light.
No.
So my question, Pierre, is: did they? And what are the implications? Thank you.
So this is a great question because it's so timely and it's so beautiful, and it also brings the conflicts that Einstein had with quantum mechanics. So Einstein was a genius. There is absolutely no question, and a lot of the work that he has done triggered quantum mechanics. But then he didn't like it because he thought quantum mechanics predicted this so-called spooky action at the distance. And I could give a talk on Bell inequalities, which are actually a lot of fun. So people have been testing this since the 1980s, really. There was, in particular, a group in France, Alain Aspect, who did beautiful experiments, but there were loopholes in these experiments. So they were kind of, people who did not believe in quantum, who don't believe in quantum mechanics could had some wiggle room. And there were three key loopholes. I don't want to go into the details of what they were. And as you pointed out a couple of months ago, a group in Delft published a paper where they removed all these loopholes and they still violate Bell's inequality. So it indicates that Einstein was indeed wrong on that. Now, what you don't know is that there are two other papers which will be published in the journal, which I'm the editor of. They will be published next week or the week after week in a journal called Physical Review Letters, which are confirming completely the Delft experiments. There's an experiment coming out of Vienna, and an experiment coming out of NIST, actually, NIST in Boulder. And the thing which is really impressive is that, you know, you always have to figure out your errors, your uncertainties, and all these things in this experiment. And they've done that extremely carefully. And now there is only one chance in 10 to the 31 that Einstein is still right. So it's not good for Einstein. Now, there are a couple of philosophical loopholes that cannot be tested in physics. So at this point, it becomes, in a sense, almost religion if you want to go past that. But these beautiful experiments from Delft and from Vienna and from NIST kind of put the nail on this thing. Now, I said that Einstein was wrong, and he was, but he was wrong in an extraordinarily interesting way. And he asked the right question. And he had the right issue with quantum mechanics. And it took, I don't remember when his EPR paper was written. Was it in the 30s? I don't remember, 32 maybe. And it took until now, it took almost 80 years to nail that down. But in the process, it opened extraordinary new developments which don't exist yet, but will probably exist in a few years, like quantum information science, quantum computers, which will be extraordinarily powerful if they ever happen. So again, you ask questions, you ask simple questions, and you create all this amount of knowledge, and as I said, you have a lot of fun doing it. So great question.
We know that two clocks moving in relationship to each other will be running at different speeds, right, from Einstein. We also know that galaxies are moving away from us, right, due to the expansion of the universe.
Right.
In Brian Greene's book, Fabric of the Cosmos, he talks about the clocks, though, in other galaxies synchronized with us because they're actually stationary with our galaxy. It's the space in between us that's expanding.
Yeah.
And I can't grasp that at all. Can you? Can you help me out?
Probably not. Not really. It's again this completely counterintuitive things, because the speed of light is constant, but what is changing is the shape of space. So the space is getting curved, and the biggest curvature is the black hole, where it goes, everything goes in. Right? So these galaxies go away from our galaxy, and we see that by looking at spectral lines. You know what spectral lines is? They're the fingerprints of atoms, right? So atoms emit light at very specific wavelengths, and because these galaxies are moving away at some speed, there's a Doppler shift, very much like when an ambulance drives by you, but for light. And by measuring this Doppler shift, you know how fast these galaxies are going away. And if you believe in the Big Bang theory, you also know where they are, right? But the clocks can be synchronized nonetheless. You can synchronize the clock on a satellite and the clock in your car. You just have to know what corrections to make. But it's really not trivial, and I didn't try to tell you that it's trivial. I think, yeah.
We got a question in the back, all the way. And after this question, we'll take one more. We know it's getting late.
Thank you. I worked in the telephone industry for about 40 years, and all digital components of a telephone switch had to be synchronized, right, so that the data or the voice would appear at the far end as it should. Those switches, telephone switches, were initially timed, synced by a cesium beam atomic clock in a cave in Missouri. And then that synchronization was distributed to 12 regional AT&T switches, and then from there to all the smaller switches in the country. Well, in the late 90s, even our small telephone company ditched that idea and started taking our synchronization from the cesium beam atomic clocks and the GPS satellites. And it's worked very well. And we did, if we lost that, we did have rubidium oscillators as a secondary source, and then we'd have a lesser quality oscillator for a third source.
Yeah, it's amazing. This time synchronization is really important. And I was actually at NIST not very long ago. I was on a review panel for some of the programs at NIST, which have to do with the clock. And they have this crazy clock, okay, which actually does not define the standard time, because to define the standard time, you have to have every country agree, and they have to have clocks, which takes a long time. But anyway, I was in this clock division, and in this clock division, there were people working on smart grid. And I asked, why smart grid? Why do the smart grid people have to work with the clock people? And it turns out it's exactly the same thing, that if you want to connect different electric networks, you need to synchronize things just right so that everything comes in phase. And because you don't want your voltage coming from TEP to suddenly be exactly out of phase with the voltage coming from APS, right? It has to all be the same. All the electrons have to wiggle exactly, synchronize with each other. And I understand that, okay? Now we have 60 hertz, right? So I say, okay, well, you need maybe hundredths of a second or thousandths of a second. It turns out they need a microsecond synchronization for these systems to work. So they also use atomic clocks for synchronization. It's everywhere, so in the phone it's even more. Yeah, thank you.
And one last question. I'll take it. How did you get interested in doing physics? And optics?
So physics, basically the reason I studied physics is that I was a kid in Switzerland, and Switzerland was a very funny country this time, because the schools in a sense were very elitist, and not elitist in the fashion of rich people. My father was a metal worker. But when I was 10 years old, they decided for some reason that I was smart. And so they put me in a different school, and when I was 12, they made me take some more tests, and they said I was smart enough to do science. So they put me for the small region of Switzerland. There were 6 of us who were put in this class to do science. And so we were doing 2 hours of math every day. So my social life was great. And so when I was 18, I had to decide what to do. And the reason I studied physics, because they told us it was the hardest one. That's the reason I did it. And out of the 6 kids which were in my class, 3 became physicists, actually. And one went to the dark side, became a chemist. And one became an engineer, and one a mathematician. So it was kind of, but I don't think they do that anymore, because they've realized in the meantime that 10 years old is a bit young to decide what kids can do and cannot do. And then why optics? So this is a bit more personal. The reason is that I can see only with one eye, and I kind of wanted to understand optics. That's all. So.
Well, join me again in thanking Pierre for coming out tonight. Awesome talk. And if you want a good laugh, you can watch this again on that YouTube channel. Have a great night. We hope to see you back in December. And if you have evaluations, you can leave them with me or Barbara or on the table where all our materials are. So have a happy Thanksgiving.